Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about integrating sphere. So let's dive right into it. Now first we have to understand why exactly do we have need of this integrating sphere. Well, reality is we need to measure light. Well, light measurement is far more difficult than you will think, because what we are aware of is like you buy a multimeter, you test voltage, you test amps and all that jazz, you go home. You may think the same thing about light meters. It's like, hey, I'm gonna buy a lux meter, I'm gonna turn it on and I'm gonna measure things. Well, yeah, it's not as simple. And on top of that, data that you need you will get out of any system is very precious for many cases, especially for safety. For example, every nation has a clear-cut data point for how safe a workplace should be or a place of people should be. For example, a pedestrian crossing should have this much lighting area. Highway at this kind of speed limit must have this kind of illumination per meter square. There are data points like that all across the world. For example, how well lit your basically warehouse should be, how well lit your machine shop should be. All these data helps us to make a workplace safe for safety of people. And the problem with human eyes is that it's very adaptive. It will try its best to give you a very good image, quote unquote, no matter the lightness. Consequence of that is like you will not notice that you are in a badly lit scenario. So that's why we need a proper way of testing light fixtures, because well, our eyes are really not that good at it. And total efficiency testing, that is also a very critical aspect. For example, till this point many people assume like LEDs are very efficient, as in like 90% is like, but reality is they are very close to 50%, and some are even lower than that. Like this is the prime reason when you watch any major company dealing with indoor farming, they will never have white light, they will always have monochromatic light. And I never understood that, but now I'm after understanding the fact that monochromatic light is used in white LEDs, then it goes through phosphor layer that emits the light. But here's the real phosphor layer is not 100% efficient. It's not gonna be like, okay, 100 watts of photon went inside me, 100 watt of colored photons will come out of you. That's not gonna happen. So that also causes a very serious loss. And when you are talking about megawatts of energy, few percentage translates to a lot, and on top of that it also translates to a lot of waste heat. So for total system efficiency, you have to utilize this sort of test trick to know what exactly the situation is. Then comparison. Now this is one thing that is very desirable for every Tom, Dick and Harry, because right now if I say bulb, you will have many options. Even in LED, you can have one LED type of LED, another type of LED, another brand of LEDs, another variant of LEDs, every Tom, Dick and Harry. So in those sort of scenarios, you have to compare them. It's like, is it really good for what I want? Is it really efficient? Because you could have a system that is much more powerful, but it's bit inefficient. Let's say it's only 35% efficient compared to something that is you have to put far more of, but you have to you get more higher efficiency, let's say 45% efficient. How would you know without a proper testing system? And calibration is the, well, again, it's not a should be used by you, it should be used by the companies who are manufacturing these bulbs. That's why this integration sphere is manufactured anyway. It's like, I'm gonna say this bulb is like 1000 lumens. How the heck they know? For that reason, we have to utilize basically a calibration sphere, so to say. So let's understand the science behind it. Science is very simple. You will heard these terms like lux. Basically, if you try to buy a meter like I did, it's generally gonna say, yeah, lux meter. So lux meter is a spot reading meter. You have to understand lux simply means lumens per meter square. So if I turn this puppy on, and if I'm like, if somebody asks me, hey, what is the light output of that fixture there, I cannot just like, okay, 300 lux, 360 lux. That does not mean anything, because lux is a spot reading. It has two data points. First, the lux output, meaning if I put it here, let's say 360, and the distance. So you will, if you, any manufacturer or any salesperson is like telling you this light has like 10,000 lux, that is meaningless, 100% useless. You have to know the distance. For example, here I'm testing it and I'm getting, let's say, let's say 380. Okay, here's TT. Now I'm close to it, and it should be, wow, 700 to 800. I'm getting much higher output. So that's the whole point. You need to know the distance. So for example, at this exact same light, I'm not going to change anything, and you may have noticed even camera did not change that much. And that's the problem with human eyes. Human eye auto adjust way too well. So if you want a proper useful data out of lux, you have to take this meter, or preferably much better and much more calibrated meter. You're going to take the reading and you're going to do it multiple meters. For example, 1 meter, 2 meter, 3 meter, 4 meter, then you're gonna get a much better picture is like how bright this is. And you will notice that from any reputable manufacturer of video lights, they will always specify 1000 lux at 1 meter, 300 lux at 3 meters, so things of that nature. They will always specify distance. Lux without distance is 100% useless. Don't even waste your time on that, because I can saturate that. Like heck, I build this let's say LED bulb, and then like I'm gonna place it right here. Whoa, this is like so many lux. It's like boatload of lux. And then I'm like far away. Okay, lux is going down. Okay, it's going down more. See, only here to here lux is starting to go down. That's why you have to know the distance. Without distance, it's pointless. And because our eye auto adjust, we are really horrible at it. And you also have to understand light also has inverse square law unless it's a laser. That also makes it very complicated. So you must know distance. Lux must come with distance. Lumens simply means the total output, meaning I sent 100 watts of electrical energy, I got 30 watt of light photons output. That's it. So lumens is a total output. It does not matter where the light is going. For example, light could be going on that side, this side, rooftop, ground, does not matter. It's the output, total output of that lamp. And it must account, whichever instrument, basically integrating sphere that you are utilizing, must account for all light produced by the fixture, a lamp, every direction, 360 degree. And there is mathematics for all sort of optimal illumination of a workspace. For example, if you are a type reading light illumination, is going to specify that basically your book, wherever you're going to put your book, at that point it should be, let's say 300 lux is bright, or maybe it's too fatiguing. If like so you're reading small text, you may not want that to be that bright. That's why reading lights are not super duper bright. So you will have this sort of data everywhere around the world that will provide you proper understanding and safe environment. So that's the science behind it. Lux does not mean much without basically meters, basically distance added to it, and lumens is total output. Where how you spend it, that's up to you. You can have reflector, you can have diffusers, things of that nature to tame the light if you want to. So how these magical spheres are built? Well, it's a sphere, and you have to understand that this sphere is mathematically doing one thing very simple. It's going to take the light, mix it all up, basically light produced from all directions, because all lights are not omnidirectional. Lights, even filament bulb is not omnidirectional. It does produce light in all where, but there will be some dead spot. If you notice that the filaments, they're not like, a sphere. Filament is not a sphere. It is like a cable, so inherently it has some directionality to it. And CFL, it's like squiggly, squiggly line. LEDs, generally they are flat, so how the heck is gonna distribute that? So there is always a component of randomness in the directionality. So this puppy removes it all out. Basically it takes the light, mixes it all up, and all it gives you is total output. That's it. Don't worry about it. It's like, and you read the total output based on the lux meter. So basically you're gonna have obviously 10,000 times better variant of this coming out of one of the sports. Now you're like, wait a minute, I said this is useless, but I specified, the sphere is mixing all the light, the diameter of the sphere. That's how you can calculate the lumens. The sphere, basically how big the sphere is, like of course you're gonna assume it's 98% efficient or 100% efficient, and then you're gonna do your mathematics. It's like, if my meter is reading, let's say 10,000 lumens, and the dimension is this much, lumens I'm saying, lux, and the diameter is this much, then you can calculate the lumens output of it. So that's the whole point. A flat, that's why it's coated white. It's never painted silver color. Basically, you do not want it to act like a mirror, because mirror will not remove directionality. You want directionality to be mixed up. For that reason, it has to be flat, matte, white color. And generally the white color that I specifically chosen is elements basically that reflects all of the visible spectrum, because generally they are focused on human systems, so generally they will have absolute white. If you are focusing on more of an infrared system, you may have gold coating inside, because gold is far more reflective in infrared. So that's the whole point. And you will never have sensor that is directly looking at the light fixture. No matter what you do, sensor should not be able to see the light directly. So generally there will be detector and there will be baffle. So baffle will always protect the detector from getting what you classify as saturated. So it should not get overwhelmed. All the photons that are going there must mix around. Generally they say photon should bounce at least 15-20 times. You can calculate that based on the diameter, and there are some cos theta, sin theta kind of mathematics involved into that. Generally bigger the better. So based on that, you can make sure your detector is reading proper light output rather than being saturated by light source itself. It must have baffles, meaning if you have sensor must have a curtain around here. Of course it should allow light that is coming from all around being reflected inside. That's awesome, but should not be like, okay, I'm directly looking at the light source. That should never happen. So it has live baffles for the sensors, and ports. Generally these things have ports. Now these ports are specifically designed for different tasks. For example, it will have one lux meter port, of course. Then there will be a second system where it will be have a spectrograph. For example, how do you know the quality of light that is being generated? Again, it's an add-on function, but it's also very useful, especially if you want your eyes to last long, or basically not fatigue. So for that reason you have to have spectrum, because some LEDs that are really poor built, they really don't have good phosphor, so they'll have very spiky blue and very black kind of green and reds. So you need a spectrum graph that's to actually show you the spectrum output. So you can also have that, and you must have very good power meters. For example, if you're talking about DC system, you must have a good voltage and amp system. Basically light fixtures that are generally working in car, they will have a good power meter. Without that power meter, this system is not that useful, because all you are getting is lux. You're not getting lux per watt. So that's why generally there will be port for that. You could have like two ports bare minimum. One would be for lux, one would be for spectrograph. Generally there is third for auxiliary lamp, which helps you in calibration. So that's the build behind it. It's just a sphere, bigger the better, and its sphere is coated white, so it mixes photon much more efficiently, removes any chance of directionality. You remove all that. You have baffles in front of the sensor, so sensor does not get overwhelmed, quote unquote. And you have ports for basically going in and out of the data, extracting data. And you generally utilize a good power meter. The better, basically even for AC system, not only voltage and amps, you also must calculate VA rating, meaning power factor must be accounted for. And that's the worst part you have to understand. Many cheap LEDs have really bad power factor, generally 0.5 power factor, so they are really bad. I mean, like, you would be surprised how close it is to a freaking filament lamp because of the bad power factor. So these are generally the build behind it. Now, how do you calibrate it? I keep talking about calibration, and this is one of the things you have to understand. If you do not calibrate yourself, basically you just build that puppy. You have a sphere, you just did it. What you have is a comparative tool, meaning this tool will tell you A is better or B is better. So this is awesome. This is still at this point in time still useful tool, really helpful, but it's like, all the ratings are floating. It's like, the gap between A bulb to B bulb to C bulb, but you do not know how far they are from zero. So for that you need calibration lamp, meaning a lamp of this sort of design is created and it's gonna certified by National Bureau of Standards, and every country has it. Generally, be it India, be it Pakistan, be it America, be it Australia, generally all of them have it. In India we call it Bureau of Indian Standards. They have many institutes and many basically facilities where you can request, or you can give them your own bulb, where it's like, hey, this is the bulb that I want, can you certify it? The idea is you need one calibration point that is trustable to that government. So in case of because Indian government is the one that is deciding all the standards, power ratings and all that, it must be traceable till that point. The moment you have this sort of bulb, then you can calibrate everything out. So this bulb will be like, okay, if you're giving me 10 volts, if you're giving me 10 amps at 100 watt of output, I should give you this much of lumens output. You're gonna find out, hey, I'm getting like, let's say 10 more or 15 less, whatever have you. You're gonna be like, okay, that is my offset. That offset allows you to calibrate this puppy. Without that, this is good. This is still good. And again, with modern electronics, this is good enough where you can actually reliably use this. But if you have that calibrated lamp, at that point, absolute. At that point, if you say my bulb is, let's say, 500 lumens per watt, which is too high, but let's say you say that, done. If you have that calibration data, your data is acceptable. So this is a very critical aspect. Without that calibration, you only have relative data. With that calibration, you have absolute data. So all data will become relative to that calibration lamp, and hopefully your nation generally have a good association that is doing their job properly, because if you don't have that, you are floating. So generally all nations do that, big nations. China will also have their own association, Bureau of Standards. USA also have that. Every country has that, and they generally, like, they're so good, so precise, and like there are people whose job is like, double PhD, triple PhD, 10 years of experience, 30 years of experience, just to make sure that they're gonna calibrate this puppy to absolute hell. So that's how you need that calibration, and that's why I specified they will always have an auxiliary lamp that also is provided. And you may even request, if you're like really serious about this, you can request, hey, can you give me a 10 watt lamp, 20 watt lamp, 30 watt lamp? Like, if you have this sort of granularity in your calibration, you can be damn sure, because sensors do get behave differently. Very few sensors in this planet has like absolute linear output. So if you get that curve feeling out of that, it's like, hey, I think it's it gets saturated at such kind of lumens. You're like, hey, how the heck I get higher calibration data? And then you're like, at higher calibration my offset is bigger or smaller, then you can use that. So calibration matters a lot. Without that, you have relative data. With this, you have absolute data. So what about DIYing it? Well, a lot of people do this, well, for many reasons, specifically for basically people who are dealing with flashlights. So if you are in this sort of culture, you will see people making Lumens tube. Is rather than a sphere, is a tube. It does the same thing, and the idea is very simple. Is the easiest way to create a tool that allows you to do comparative data. If you are buying, let's say you are populating a house, or you're populating a large warehouse, if you can reliably know which bulbs are good, that saves you money, that saves you time, that saves you everything. Awesome. That only it makes things awesome. So investing even a little bit of money on getting big thermocol spheres, it's not that expensive. So people do that, and some people have taken beach balls and cover them up with a newspaper and putting and then get this paper out. Some people have 3D printed it. Go YOLO on it. It's a very simple thing. And even in this sort of environment, people are like, how about we make it more accurate? They basically generally try to find a quote unquote friend who works in this sort of association, Bureau of Standards, and they're like, can you calibrate this flash lamp? It's like, okay, this lamp is tested and calibrated. Or sometimes people buy brands that are known. Basically, if you buy a brand that is like, no, that brand is certifying it. Brand could itself have their own basically integration sphere, and they're like, no, if you are saying 500 lumens output means it has goddamn 500 lumens output, you can use that as a calibration for your sphere. And at that point in time, so if you're reading instead of 500 you are getting 450, you have 50 offset, you add 50 to whatever you're reading. So you built a lamp that says torch that says 10,000 lumens, it's 10,050 lumens. So that's the whole point. You can add calibration to that also to make an actual data point. As long as you are testing the power, you can test the efficiency. As long as you have calibration data point, you can have really amazing time. Be mindful, generally, if you are using thermocol, please cover it out with basically boatload of aluminum foil, simply because while the thermocol is going to do your reflection part, diffusion part, it still is not opaque enough. Generally, integration spheres are made out of thick metal. For that reason, photon should not just make its way into it. So that's why cover it out with aluminum foil. It's surprisingly easy. Many people have done that and do DIY integration sphere. Many people use PVC pipe because it's much easier, but you can do that. So this was my presentation on light integrating sphere. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I would have said press dislike, but good luck with that. I would urge you to comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.